Hello, good morning everyone. Am I audible? Am I audible? Okay, today we will start with this counters and registers. So counter, you might have seen this counter in railway station or like in digital clock also this type of counter is there. We will study how this is working. Okay. So counter is a sequential circuit because it output is affected by input and there is a memory because even in digital clock if we now it is 803. Okay, so it is remembering like what is the last output, then after that the next output will be 804. So it is remembering what is the previous output and the next output is related to that previous output. It is the next term. So that is a counter. So here also we are because it is a sequential circuit, here also we are using a pulse or a clock. So a digital counter which uses for counting pulse is known as a counter. A counter is a circuit that counts the binary number of occurrence of an input. Each count a binary number is called a state of a counter. Okay. So here also because we are studying digital electronics, so here the counting is in form of binary. Okay. We will study in future this is a 7 segments display. So how a binary number is converted back to a decimal number in the 7 segment display. So that we will study in the other modules. So here also we are using this binary 0 and 1, which is being converted to this decimal value. Okay. So that conversion we will study in another module that is called 7 segment display because it has 7 segments if you count here. So that we will study in future. So counter is we have this bit and this combination. Same way the counter is also same. So a counter is counting terms in n bits, which has two and different states. Okay, like this we had like one bit is there, then the number of combinations will be 2 to the power n. So 2 to the power n 2 to the power 1, so two combinations will be there. So here also if a number of bit is 2, then the combinations will be 4, and if the number of bit is 3, then the combinations will be 8. Here in the counter also, if the number of bit is n, then 2n will be different states or combinations. The number of different states of counter is known as modulus. Okay. So this 2n, it is called as modulus. Thus, an n-bit counter is a module 2n counter. Okay. Like here, this we call a counter we call as modulus. So what is modulus? This is 2 to the power n. So if number of bit is 2, then we are calling this as then the combination will be or different states will be 2 to the power n. So that will be 2. So we will call this as modulo 2. Okay. So if number of bit is 2 and the combinations are 4 or the different states are 4, so we will call it as modulo 4. So how many number of states are there or how many number of combinations are there, we name it like that. So here we have number of bit is 3, so the combination will be 8, so we will call this as modulo 8. Okay. And if 0, we have a counter from 1 to 10. Okay. So 10 numbers are there, then we will call it as modulo 10 counter. So this is the bit combination. So counter is the widest application of flip-flop. So we are using flip-flop in the count for the counters. Whatever we have studied, this T flip-flop, D flip-flop, and this JK flip-flop. So that is used in this counter. Okay. But here in for our studies, we will use this JK flip-flop. We can even do this counter with a D flip-flop, and there is one more flip-flop known as T flip-flop. But we will use a JK flip-flop for our application. So it is a group of flip-flops with a clock signal applied. Okay, how JK flip-flop is working? Same way this will also work. So any doubt in counter? What is a counter? Hello?
No, ma'am.
Okay, so this is the combinations we studied. So we have two types of counters based on this clock. Okay. So first is asynchronous counter, which we call as ripple counter. So here, what all the flip flops are not clocked simultaneously. Means we are giving one clock, and the output from here is given to the next clock. Okay. So this is a asynchronous counter, and a synchronous counter where all the flip flops are clocked simultaneously. So there will be a single clock, and each flip flop will be given a single the same clock pulse. So this is known as synchronous. Synchronous by name only, that we will know that it is in sync. Okay, everything is same. So synchronous counter means it has a same clock, and asynchronous means all flip flops are not clocked simultaneously. Means it has different clocks. So here in asynchronous, what we do, we give the clock to this first counter, and the output for this first clock, we will output from this queue, we will give it to the other counter as a clock. Okay, so this is a asynchronous counter. So we will be mainly using this asynchronous counter. The synchronous, we will not study this. We will only study this asynchronous counter, because this is easier to do any this count for this counters. This is easier method. Okay, so another type of specification of counter is up down counter. So up counter will count from 0 to n, means like 0, 1, 2, 3, 4, like that till n. And a down counter will have maximum count, means we will have first have n. Okay, and it will then decrease by 1. So we will have n, then it will have n plus 1, and then it will decrease, and it will go to 0. So this is up counter, and this is down counter. So this is asynchronous counter, because we will have this asynchronous counter. So we will be studying this asynchronous counter. Okay, so clock is connected to a flip flop clock input on least significant bit flip flop. So here, this first clock, it is connected to this least significant bit. If we go here, if we take this number, so this is there is only one number, so there will be no least significant most significant bit. Then I told you, for this number, this will be the rightmost will be least significant bit, and the leftmost will be most significant bit. And then this 3-bit counter, so this will be the least significant bit, and this will be the most significant bit. Okay, we are counting from here, but our circuit diagram is a little bit opposite, so don't get confused in that. Here we are having least significant bit. So here, the first clock we will give to least significant bit, and then we will from the output we will give it to the next clock, and from the second flip flop we will give the output to the third clock. Okay, and from here we are getting this number. This is 2 to the power 0, this is 2 to the power 1, and this is 2 to the power 2. So this is the least significant bit, and this is the most significant bit. Okay, so this is how we are constructing the circuit for asynchronous counter. For 1 bit, there will be only one flip flop. Okay, for 2 bits, there will be two flip flop, and this is a 3-bit asynchronous counter. So we have, that's why we have three flip flops. And if we had four, then we would have four flip flops. So this is how we will do the counting. So for all other bits of flip-flop, output is connected to the clock input, thus the circuit is not truly synchronous. So that's why it is like output is going to the input of the clock. So that is why it is not synchronous. A common clock is not there. So output changes are delayed more for each bit towards the MSB. We will see how this is working. Okay, we'll see how this is working. So you just have to make a JK flip flop. So you remember JK flip flop, it has a clock, two JKs, Q and Q bar is there. So first clock will be there, and the output is going to the second clock. So this will be the least significant bit, and this will be the 2 to the power 1, and this will be the 2 to the power 2. And JK, it is connected to 1. All the JK is connected to 1, so this is the circuit. I will tell you why it is connected to 1. So here we have 3-bit up counter with negative edge trigger JK bistable. Okay, first I will explain you clock. So I told you clock is a digital pulse with 1 and 0. So same way we have clock. Okay. So this is not in syllabus, but you need to understand this. So a clock pulse is continuously changing signal that oscillates between high state and low state. So this is high state and this is low state. So it is constantly changing. So this is a digital pulse. Okay. So a common type of clock signal is a square type. So you can see it is a square type of signal. So which has 50% duty cycle. Okay. So 50% duty cycle, it means half of the time it will be high. So 50 means half. Okay. So half of the time it will be high and half of the time it will be low. So this is 50% duty cycle with a fixed and constant frequency. So all the pulse width are same, so the frequency is also same. Okay. So we have two types of clock pulse. One is positive edge triggering and one is negative edge triggering. So earlier what we did in JK flip flop and D flip flop, we used positive edge triggering. Okay. So output will respond to the change in the input only with positive edge. So this is the positive edge and this is the negative edge. Okay. This part is the negative edge. So whenever this positive edge is coming, only then our JK flip flop is working. So that is a positive edge triggering. Means if positive edge triggering, it means that when it is a 1, only then our flip flop is working. Okay. So JK flip flop, D flip flop was all positive edge triggering. But here in this counter, everything is negative edge triggering. So negative edge triggering means this falling edge of the signal. Okay, this falling edge of the signal. It means it will work only when we have a 0. When the clock is 0, it will work at that time. So the output responds to the changes in input only at the negative edge of the clock pulse. Okay, that is when we are having a logic 0. Any doubt in this positive edge triggering and negative edge triggering?
No, ma'am.
Okay. So in JK flip flop, we were using this positive edge triggering, but here we will be using a negative edge triggering over here. Okay. So this is 3-bit up counter with negative edge JK bistable. Okay. So I will first explain you how we are using this JK bistable. So this is how this JK bistable is working. Okay. So we have to see this condition for this 1 1. Okay. We are using this condition of 1 1. So if I open my JK bistable, so yesterday I explained this JK bistable preset and clear. We have to put it at 1 1. But because this is positive S triggering, we are using this as 0 0. Here you can see there is a bubble. It means it is a negative edge triggering. So we have to first preset and clear this as 1 1. Okay. So that is a enable key. Only then our this JK bistable will work, and then we will start using this J and K. So here JK, actually we are using this JK as I will just explain this JK once. So first we have to, so in JK we have JK as input, there is a clock as input, and we have extra as preset and clear. This preset and clear is to enable our circuit, okay, and Q and Q dash is the output. So first we will see this preset and clear. It will work similarly as this part, our SR NOR gate, or 00, it is a memory, so we are not using this. For 01, we will get a 0 output. So I will do this for 0 preset and clear. For 01, we will get a 0 output. So this is because this is negative edge triggering, we are getting opposite. So Q, we are getting it as 1. So for 1 0, and this is negative edge triggering, and this is our positive edge triggering. So we are getting it opposite. So for 1 0, we will get 1, but we will get opposite. For 1 0, we will get a 1. And for 1 1, this JK flip flop, it will get enabled. But here we have this as a negative edge triggered, and in Logisim, we are having this positive edge triggered because we don't have a bubble here in preset and clear. So this condition 1 1, it is starting the circuit, means it is enabling the JK flip flop, okay. So but here, because it is positive edge triggering, our is 0 0, and we have to put enable as 1. So this is how we are starting this circuit. Then it will work similarly as how SR NOR gate is working, but here we have to do with clock. So for 0 1, this Q will work, but we have to give input as clock. So Q is 0 and Q dash is 1. So we are getting the same output. So Q is the main output, so Q is reset. So for 1 0, we have to again change the clock. So after we change it, then it is remaining same, means this is the final output of this one. Then Q is 1, so it is working same as this RS NOR gate. And for 0 0, it is acting as a memory. Okay, for 0 0, whatever the output was there, it is working same. Output is same. But for 1 1, we can see it is a Q bar. Okay, so if we give here as 1 1, and if we change the clock, whatever the value of Q is there, it will just become opposite. Okay, so it is positive edge triggering. So whenever we are giving a 1, only then it is changing. Then we are going back to 0, it is not changing. So again there is 1 1. Okay, so again it will give Q dash. So whatever the original output was, so it will just reverse it. Again it will give 1, it will give opposite, so it is 1 0. So again if we give 0, then it is not working. So again it will give 1, because this is positive edge triggering, we will get a 0. Okay, so it is like reversing every time. So whenever we are changing the clock to positive edge, this Q is changing, it is just becoming opposite. So that's why we are using this JK flip flop for our circuit. Okay, so here we are using this JK flip flop for a counter. I will tell you how this will work. So we have 3-bit ripple counter, 3 flip flops will be used. So how many bit is there, that many flip flops will be used. As n is the, here n value is 3, so the counter can count up to 2 to the power 8. So we can call it module 8. So I told you now, with JK as 1 1, we are seeing that the values are getting updated. So that's why we are using this logic 1, because it is flipping again and again. So we will use that flipping as counting. Okay, so that's why for both J and K, we are using input as 1. So all JK must be logic 1 to enable the binary counting. So clock connected to the flip-flop input of LSB flip-flop. So clock is connected to this least significant bit. So this is the least significant bit, and this is the most significant bit. Okay. So output change is delayed more for each bit towards the most significant bit. So like I will explain this. So 3-bit counter is there. So it will start from 000, then it will go from to 001, then 010, 011, like that it will go. And finally, if it comes back to 111, it is switching back to 000. Okay. It is switching back to 000. So this is a module 8 counter. So how this is counting? Actually, for this Q0, our first flip flop is working, and this Q1, the second flip flop is working, and this Q2, this third flip flop is working. Okay. So as I am changing from what I am doing, I am changing from zero. If you see the truth table for this, so it is changing every next time. It is changing every next time, but here it is changing after 2 times. Here 00 is coming, 11 is coming, then again 00 is coming, then 11 is coming. Okay. So for, then here we can see that 4 zeros are there and then 4 ones are coming. So here if we give a clock, and first we will see that we have given a 0. Okay. So it is JK flip flop. So this first flip flop, it will work. So as we are giving this first clock pulse and it is negative S triggered, so we are giving a 0. So here it is negative S triggered. So here it is changing back to 1. Okay, here that's why it is changing back to 1 until next clock is 0. So that's why we are it is only staying till 1. Okay. So then the next clock pulse is coming, it is changing back to 0. So here you can see the output for this clock, it is output for this JK flip flop, it is going to the input of this clock. Okay. So for this clock, this output is working as a clock. And for output from here, it is given to this clock. So here this output will work as a clock for here. So as it is negative S triggering, so this is the clock for this Q1. Okay, this second flip flop. So here you can say this is negative S triggered. So whenever we are getting a down, then initially we are given a 0, so it will change. Okay. Then again the second negative edge triggering is occurring here, so again it will change. That's why it is 2 times it is coming as 00 and 2 times it is coming as 11, then again 00 and then again 11. Okay. And if we see here for third clock, here the output is working as an input for this clock. So uh, this is working as a clock for this flip flop. So for a third part, this is working as a clock. So we will give a 0. So it doesn't change with this clock. It will change with this clock. Okay. So whenever the change is coming, so here the negative S triggering, first negative S triggering is coming. Only here this will change. So it will become our 1. So this is how we are getting a Q0, and this is how we are getting a Q1, and this is how we are getting a Q2. Any doubt? Any doubt in how we are doing the operation?
No, ma'am.
Okay, we will do this simulation. So actually here in this logisim, we have 8-bit counter. Okay. So for counting down, we have to give it as 0. So we will change the clock. Okay. So this is actually, I think, positive S triggering. So mm. So this is for our positive S triggering, and so this should be 1. and this is for counting. Okay, so it will both work as up counter and down counter. So initially our count is all zeros. This is 8-bit counter, so everything is 0. So I should so initially all the values will be 0. Okay, so this 0 here is for up counter, and if we give it as 1, then it will become a down counter. Okay, so this is positive edge triggering. I don't know whether it will work in negative. No, it will not work in negative. So this is a positive edge triggering counter. Okay, so whenever we are getting a 1, it is changing. So this is becoming 1, then again it is becoming 0 1 0. Okay, and for third clock it is becoming 0 1 1, and for counter it is becoming 1 0 0, and then fifth it is becoming 1 0 1. So this is an up counter. So if we give it as 1, it becomes a down counter. So if we start giving the clock, you can see it is decreasing, and it will go back to 0, and after 0 it will go back to the last value. So for 8-bit last values, all 8 ones. So this is how it is decreasing, and this is a up counter. So we can see this last value, it is changing like every next value. It is changing for every next value. So we are using this first flip flop for this. Okay, then the output for this first flip flop, the output for this first flip flop is the input of this clock. So this second this q1, it will get affected. This is the clock for the second flip flop. So whenever there is negative edge triggering, only then our this will change. Because I told you na, in jk flip flop, if we give 1 1, we can see it is just reversing from 0 to 1. So we are using this concept. And for the third, this will work as the input clock. So here is the negative edge triggering. So wherever we are getting a 0, over here it is changing to 1. So this is how 3-bit counter is working. Okay, so this will come in exam, 3-bit up counter. Remember everything, this part, 3-bit up counter, and this part. You have to write this part. So for a 4-stage binary counter, we are having this 4 flip-flops. Okay. Here is the least significant bit, and here is the most significant bit. So if we see here, this is the least significant bit, and here is the most significant bit, but the circuit is little bit opposite. And JK again we are giving as 1, and here this part is used to calculate these numbers, first numbers. So it is changing with every other clock. And here the output for here is the here the input for this clock is the output from first jk flip flop. So it is changing with this part whenever we are getting a first negative, so it is changing with that. And for this input for this clock, third flip flop is the output from the second clock. So this is the clock for this third flip flop. So it is changing whenever we are getting a negative edge. So it is changing with that. And for this fourth part, the output for this from this third flip flop is the input to this clock. So it is changing. So this is the clock for this fourth one. So it is changing whenever we are getting a negative. Okay. So this is how we are constructing this 4-bit flip flop. The theory will be same. Each stage successively divides the clock input signal by a factor of 2. Okay, because it is delaying every time. So we are giving a logic 1 for this both JK because with JK as 1, it is toggling. So here JK inputs must be taken as logic 0 because it enables the counting. So because this JK is 1 1, so it starts toggling this first part. Then again we have another clock, then this starts toggling, then this starts toggling. So clock is connected to the flip-flop input on the least significant bit of the flip-flop. Okay, this clock is connected to this least significant bit. So you can just construct a diagram and just you can explain this. We are having 4 JK flip-flops. This JK flip-flop is 1. The clock is connected to this least significant bit, and the output for this first flip-flop is the input for the second flip-flop. Okay. So because here our clock will get delayed, then again here we will clock will get more delayed by 2, and here the clock will be delayed by 4, and here the clock will be delayed by 8. So that's why here it is written. Here you can say the clock, here we have two clocks, so for two clocks we are having only one clock, but for here we for two clocks we are having here for four clocks we are having only two one clock, and here for 8 clock we are having only one clock. So this is how all the counting is getting delayed, and this is how we are counting. Okay, so with each flip flop our counter is getting delayed. So this is how we are doing the counting. So output changes is delayed more with each bit towards the most significant bit. So with each flip flop the counting is getting delayed. So this is the timing diagram which I explained. So here we will give the first clock. So initially we are giving Q as everything as 0. This QA, QB, QC, QD. So here with first negative edge triggering, this JK will toggle. So it will become 1. So here we have second negative edge triggering. So it will again toggle and it will go to 0. So this is how we are getting this 0, 1, 0, 1, 0, 1 like this. Then for this QB, this is the clock for this QB. So with here we can see this is the first negative edge triggering. So it will change from 0 to 1. Then here is the second edge triggering. So it will go from 1 to 0. Here the third part is there. So it will go from 0 to 1. And for QC, this is the input clock. So here we have given 0 and no negative edge triggering is coming. So here is the first negative edge triggering. So it will go from 0 to 1. Here is the negative edge triggering. So it will go from 1 to 0. And here the third is there. So it is going from 0 to 1. Okay. And for QD, this is the input clock. So whenever we will, initially it will all go to 0, and here the first negative edge triggering is there. So it will go from 0 to 1, and here is the second negative edge triggering. So it will go from 1 to 0 here. Any doubt in this?
Ma'am,
Waveform.
why should the J and K values must be 1?
See here what we are doing, we have to change it from 0 to 1. Okay, we have to change it from 0 to 1. So if we go to this JK flip flop, okay, so we have to change it from 0 to 1 with each clock. So here for JK flip flop, for this 1 1 it is Q bar. Okay, so wherever it is 1 1 and Q bar means it will become opposite. If it is 0 then it will become 1, and if it will is 1 then it will become 0. So it will just become opposite. Okay, I will show you in this JK flip flop with each clock. So this is positive as triggered. So with every one, you can see the value of Q is 1 and Q bar is 0. Okay. So with each clock, it is changing. With whenever we are giving it a 1, it is changing to 0. It is just becoming opposite. So we are using this factor. Again, it changed to 1, from 0 to 1. Then again, if we change, then it is going back to 0. So we are using this toggling effect for our counter.
Okay, ma'am.
Okay. One more person was asking.
Waveform.
Hmm.
Waveform for JK bus table.
This part.
We have to write this part, ma'am.
Yes. Like with each negative edge triggering, you just increase a 1. Okay. So
Sure.
we saw now whenever we are giving a 1, it is changing from 0 to 1, 0 to 1. Okay, JK.
Okay, ma'am.
So here what it is happening, uh, for this we are giving a clock. Okay, for this we are giving a clock, but here for second, actually we have to delay this only by one factor na. You can see here in the truth table it is only changing from 0 to 1, 0 to 1, like it is changing only by one. Okay, one factor. But here we can see in the second bit number, we will say that two zeros are coming and two ones are coming, then two zeros are coming and two ones are coming. But in the third bit we are getting four zeros and four ones. Okay, four zeros and four ones. And then here we are getting eight zeros and eight ones, eight zeros and eight ones. So what we will do, for this part we will initially use this clock. So for this part we will use this clock. Okay, but what it is only delayed by one. It is delayed by one. For this second flip flop, for this second number, for this second number it is delayed by 2. So what we have done, we have used the output for this as a clock for this input. You can see in the circuit, the output from this first flip flop we have used as a clock. Okay, so whenever this is changing, then only this third part will change. And for this part, we can see that the output from here, it is going back to the clock of this. So whenever this Q0 is changing, whenever this part is changing, then this part will change, okay, with negative is triggering. And for the last part, this output will be the clock for this. So whenever this is changing, only then this will change. So see, it is negative edge triggering now. So here also, if I show you in this counter, first I will show you JK flip flop. With each clock, it is changing. Like we have to give full clock, then only it will change. Like clock has two sides, na, 0 and 1. So whenever we are giving a 1, only then it will change. With 0, it is not changing. So this is negative edge triggering.
Ma'am,
Hmm.
in syllabus only negative edge JK stable is there, na ma'am?
Yes. Negative is there.
Ma'am, explain fifth question in assignment.
Hmm?
Fifth question in assignment.
Fifth question. This you understood? The
Yes,
person who
ma'am.
didn't understand, that person?
Yes, ma'am. Understood.
Okay.
Understood, ma'am.
This fifth question. This is not coming in exam, but I will explain it. Okay. So a logic arrangement has to be designed so it produces a pulse train. Devise a logic circuit arrangement that will generate the pulse train from a regular square wave input. Okay, like there is a certain logic. I don't think this is applicable to you, but they have given this question. So this is the input and this is the output. Okay, so this is also negative edge triggering. There is a mistake in the book. So here we will put JK as 1 and here we are giving the clock. So here one clock is going here and one another clock is going to the NAND gate. Okay. So here what is happening to this QA, it is getting delayed, and in QB it is again getting delayed by 2. It is getting delayed by 1 for QA and it is getting delayed by 2. Okay, so here we are getting this signal, and then what we have done, we have NAND gate this signal and then we have NAND gated this signal. This you understood na, there is a delay similar to our counter
Yes, ma'am. Put uh,
here and here.
output.
What
I didn't understand.
delay you understood, how the counter's
Yes,
delay is
ma'am.
working, this
Yes,
part
ma'am.
delay. The same thing is working over here. Whenever we are getting a negative, it is changing the state from 0 to 1. And again, we are getting a negative, it is changing from 0 to 1. Okay. This you understood, na? How it is changing?
Yes, ma'am.
So for this second part, we are using this part na, as a clock. So we are using QA as a clock for this. So whenever we are getting a negative S triggering, then it is changing. Okay. So here it is getting delayed by 1, and here it is getting delayed by 2. This you understood, na? So this is the clock. So initially we are giving a 0. So 0 is there. So whenever this negative edge is there, then it is changing back to 1. Then again it is being 1, and this is the clock. So whenever we are getting a negative, then it is going back to 0.
Yes,
Okay.
ma'am.
This part you understood?
Yes, ma'am.
Q and QB. Then here this NAND gate is there. Okay. So here we are directly taking the input. This you understood? So this is the input. This part and this part we are putting it in NAND gate.
Yes, ma'am.
Okay. So what is the truth table for NAND gate?
It is opposite
Truth
to
table
AND
for,
gate.
sorry, this is NAND. Sorry, this is
AND gate.
AND gate. Sorry. Sorry. This is AND gate. So what is the truth table for AND gate? You remember truth table for AND gate? 00011011. What is AND?
It will
Binary
produce the
multiplication of.
logic 1 if all the inputs are at logic 1. Otherwise, the output will be 0.
So for 00 we will get a 0. For 01 we will get a 0. Only 1 we will get a 1. Okay, because it is product of both A and B. So here they have NAND gate this AND gated this signal and AND gated this signal. Okay, so any 1 0 is there, it will completely become 0. So here you can see uh, so here you can see there is a 0 and there is a 1. So that's why here we are getting a 0. Okay, but here we are having a 0 and here we are having a 1. So we are multiplying both the signals. So because of that here we are getting a 0. And you can see here we are having a 1 and here also we are having a 1. That's why we are getting a 1 here. Then again we are having a 0, so we are getting a 0 here. And again we are having a 1 and here we are having a 1, so we are getting 1 here. Then everything is 0, so we will get a 0. Okay, then here we are having a 1, but here we are having a 0. So that's why we are getting a 0. Then we are having a 1 here, and this this 1 is here, so we are getting a 1 here. Then again there is a 0, so here there is a 0, so here we are getting a 1. But at the last we are getting a 1, and here also 1 is there. So 1 into 1 we are getting a 1. So this is how we are getting the circuit.
Okay, ma'am.
So actually it is a very advanced level question. Okay, I don't think this will come in exam. It is not coming in the internals, but this can come like if you have to remember the circuit, the circuit. Anyone has any doubt in the circuit?
No, ma'am.
Ma'am, is the answer for the fifth one?
Hmm.
Is this circuit the answer for the fifth one?
Yes, this is the circuit. This is the question, and this is the circuit.
Ma'am, do we need to draw this square wave too?
This part. This
Only
is
the
not
circuit is enough, right?
this is not coming in internals, but if you get it in externals, so you have to remember the circuit. I don't think they will ask any other circuit. Okay, like this is very advanced level study. This won't come, but because this is in the book, this might come in
Only the
externals.
circuit. Ma'am.
This part only it will come. Others it won't come because this is like a little bit logical. Logical circuit is there, so I don't think it will come in the exam in the internals. In external, if it comes, then this question, particular question will come. Any other question, it won't come. Okay.
Okay, ma'am.
So shift registers, I will start it tomorrow. Okay. Or should I start it today?
Tomorrow, ma'am.
You understood how this counter is working? Uh, if you don't have any doubt, then you can write your roll number and leave. And for this shift registers, I gave you a question. There is a change in the question, so this CISO is coming. Okay. So if you can read this CISO part, shift and shift out, and complete the assignments. Only CISO is left, so I have given it in the PPT. So you uh, complete it by seeing the PPT and submit it by today.
Ma'am, second question in the PPT.
Hmm?
Second question in the PPT. Out of.
If you go to the video lectures of last time, you can find it. I have explained it like 2-3 times.
Ma'am, do we have to answer all the questions in the assignment?
Ah, yes.
Ma'am, what about 18th question, ma'am?
1 minute. What is the 18th question? A
It is
simulation.
about logism. We should do.
So do the simulation in Logisim or you do it in Logic Simulator in your mobile.
How should we submit that, ma'am?
Just take the screenshots and compile it.
Okay, ma'am.
Okay. Just take the screenshots and compile it. So that question, it is this is coming in exam. So study this part. So this question. It has been reversed little bit. Like to operate the lamp switch A, B, and C must be operated. So we can see that we have 3 switches. Okay. So 3 inputs are there. A, B, C. So if 3 inputs are there, what is the combination? It will be 0, 0, 0, 0, 0, 1, 0, 1, 0. So this is the combination. Okay. The person who has the doubt.
Ma'am, they give A and either B or C, ma'am.
So inputs are switch A, switch B, and switch C. So 3 inputs are there. So A, B, C is the input. Okay. So a type of combinations will be there. This you understood?
Yes, ma'am.
Okay. So what it has given, a logic circuit is to be constructed whenever it will produce a logic 1 whenever 2 or more of the 3 inputs are logic 1. Okay. So whenever 2 or more inputs, okay, inputs are logic 1, 2 or 3 inputs, then only we will get a 1. So here, if we see this combination, you understand, it is coming 0, 0, 0, 0, 0, 1, 0, 1, 0. These are the
Yes,
input
ma'am.
combinations. So whenever there are 2 or more ones, only then we will get a 1. Okay. So for first condition 0, 0, 0, we are only getting a 0. Then for second condition 0, 0, 1, because only 1 is there. We need 2 or more. Okay. So we will give a 0. So it will produce a logic 1 whenever 2 or more of the 3 inputs are logic 0. So here 2 are not there. So that's why we are giving a 0. Okay. So for this condition, we can see it is coming as 0, 1, 1. So here we have two ones. So we will get a 1 here. Okay.
Yes, ma'am.
But for this next condition, it is 1, 0, 0. So here we are getting a 0. So here for 1, 0, 1, here two ones are there. That's why we are getting a 1. For 110, we two ones are there. That's why we are getting a 1. And for 111, again three ones are there. That's why we are getting a 1. Okay. So if you go to this full adder, you can see this is carry gate. So we are having 0001 and 0111. If we go here, see, we are getting 0001 and 0111. Okay. Understood this part?
Yes, ma'am. Yes, ma'am.
Ma'am,
So you remember how? Huh,
ma'am, which circuits we have to construct in logism?
all the circuits.
All the circuits means you taught now.
Whatever are there,
Today,
that is just for your reference. Okay. If you do the higher circuits like this counters and all, that will be good.
okay, ma'am.
Like full adder, half adder,
Negative edge we can't
multiplexer. It is for
construct,
your
no, ma'am.
understanding. So do
Okay,
positive
ma'am.
edge. Just see the video lectures what I have done. So do
Okay,
that.
ma'am.
Ma'am, what about microcontroller? It has not been done yet. Does the question has to be answered?
No, no. We microcontroller is not in the syllabus. I have sent a syllabus copy na in the group, and that microcontroller is not there, so it is not coming. So how we will simplify this carry gate? So wherever we are getting a 1, we will take all the inputs for this. Okay. So we will call it as min term. So here we are getting a 1, here we are getting a 1, here we are getting a 1, and here we are getting a 1. Okay. So we will use sum of products. So first, wherever we are getting a 1, we will product all the inputs. Okay. So for here we are getting a 1, it will become 0, 1, 1 is the input. So this, because 0 is there, we will do a dash or a bar. So a bar into b into c. For here we will do, it is 101. So we will do a into b bar into c. Here is the third term. So we will do a into b into c bar, because 110 is there. And here 111 is there. Then that's why we are getting abc. Okay. So we have done the products. Then we are applying the sum of products. So we will add all the products. Okay, so that will become a sum. So if we simplify this equation, it is coming to ab into ac into bc. So this you don't have to remember. Understood this part?
Yes, ma'am.
So here in the book, what they have done, for getting the products, first we are getting the products, they have eliminated wherever we are getting a 0. Okay, they have only taken ones. So here you will get a BC. Here for the second case, you will get AC, and here for third case you will get AB, and here for last case you will get ABC. So y will become BC into AC into AB into ABC. Because ABC everything is 1, so we are eliminating this part. Or if you do common as AB, then you will get 1 plus C. So in simplification, 1 plus C equal to 1. Okay, that's why finally we are getting AC in plus AB into BC. So this is the circuit. This first AND gate is for AC, so we are taking a and we are taking a C. This AND gate is for AB, so we are taking a and we are taking a B from here. And this is for BC. So here we are taking a B, and from here we are taking a C. So we got this part, and this part. So here we can see a plus. So we have used a OR gate. So we are using a OR gate. So final coming is AC plus AB plus BC. Okay.
Yes, ma'am.
Okay, you can write your roll numbers and leave.
Ma'am, so the circuits that we create in Logism, the screenshots of those has to be attached in the PDF.
Yes.
And the question of microcontroller need not be answered, ma'am.
No. That is not there.
Okay, ma'am.